All right, you crazy kids, here's your lecture on calculating enthalpy. Before we start, a couple things. First, heat is the energy transfer between samples of matter. Heat of reaction, that is the quantity of energy released or absorbed as heat during a chemical reaction. That should sound familiar because that's actually the change in enthalpy. Those mean the same thing. And when I add heat to my regular reaction, it turns into what we call a thermochemical reaction. Isn't that fancy? All you're doing is either adding heat as a reactant or a product. In this case, I've added it as a product. If heat is a product, that means it's exothermic. Really big mistake that students make a lot of times. They see that this is positive 483.6 kilojoules. Remember that the enthalpy change is negative 483.6 kilojoules. All right. When things are exothermic, they give off energy. We show that as a negative enthalpy change in chemistry. It's just one of those things. Now, a couple other things. Coefficients are molar ratios. So this literally reads 2 moles of hydrogen and a mole of oxygen create 2 moles of water and give off 483.6 kilojoules of energy in that process. If I wanted to figure out what's the amount of energy per mole of water, because right now it's 2 moles, right? So this is for 2 moles of water produced. I could divide this whole thing by 2, and the entire thing includes the energy. So when I divide by 2, it turns into 1 mole of hydrogen and half a mole of oxygen produce 1 mole of water and 241.8 kilojoules of energy. Notice how my heat has actually been cut in half. That's because it is connected with those molar ratios. All right, so if I have 2 moles of water being produced, this is the energy. Now if I only have 1 mole, it's half the amount of energy. That should kind of make sense. Don't worry about this half, all right? Fractional amounts are now cool. We are dealing with molar amounts, so it's totally reasonable to have half a mole of oxygen. No big deal. All right, enthalpy. The change in enthalpy, the amount of energy lost or absorbed by a system as heat during a process or a chemical reaction. We used this formula when we did potential energy diagrams. Believe it or not, that formula has a name. That's called Hess's law. Hess's law specifically is the change in enthalpy of the reaction is the sum of the enthalpy of your products minus the sum of the enthalpy of the reactants. That's how that works. Just as a remembering thing, all right, if it's negative, that's exothermic. That means energy is given off. All right, that's like A plus B yields C plus heat. Okay, you can only add things to a chemical reaction. So in this case, I've added the heat as a product, even though the enthalpy change is negative. Just the opposite of that, if you get a positive value, that's endothermic. That means you'd have heat plus A plus B yields C. Notice that I've added it as a reactant. You can only add things to chemical reactions. You cannot subtract things, which is one of those things. It does not work. All right, we're jumping into it now. We are going to be calculating the enthalpy change of this reaction, shown here, using Hess's law, shown here. To do that, we're going to use what's called standard heats of formation. Now, standard heats of formation has a definition right here. The change in enthalpy that accompanies the formation of 1 mole of the compound in their standard state from its elements in their standard states. That sounds a little bit weird, but don't worry about it too much. All that's saying is that if you want to make a compound like CO2, you would use the elements that make CO2, carbon and oxygen. The fun part here is that it has to be 1 mole of the product. I've only had 1 mole of the product here. And I have to use compounds and elements in their standard states. Standard states just means the state of matter at room temperature. So carbon would be a solid, oxygen would be a gas, and CO2 would also be a gas. So it's actually not that scary after all. It's important to note that the standard heat of formation of individual elements is 0. All right, they're free. They're already out there. You don't have to figure out how much energy it took to create them because they're already there. These standard heats of formation are in table F. If you don't have table F with you, you can literally just Google it. These are all known values. It's not something you would have to calculate. It's something you look up. So in table F, if you were to look up CH4, you get that value. Whoops. You get that value. If you look up CO2, and it's important to note CH4 in the gaseous state, CO2 in the gaseous state, you're going to get that value. And H2O in the liquid state here, you get that value. If you try to look up O2, you can't because it's an element. Remember, free elements and their standard states are 0, so they're not going to be involved in our calculation. Now that we have those values, what we're going to do is plug it into Hess's law. So here we have our products These are our product values. That's going to go in there. And we have our reactants. And these are our reactants value. That's going to go in there. Let's see what it looks like. All right. A couple things of note. I have my 393.5 kilojoules. 393.5 kilojoules, no big deal, negative. But it looks like I have 2 times my 285.8 kilojoules. That's because of this coefficient. All right, these are molar amounts. It's the formation of 1 mole of the compound. So that's per mole, that's the energy per mole. Here I have 2 moles, so I had to double that value in my calculation. Important. On the other side of the equation, I have my negative 74.8 kilojoules shown here. I've left out this 0. If you really want to, you can add it in there, but it's not going to change your answer, so it doesn't matter. And when I plug this into my calculator, I get my enthalpy of a reaction is negative 890.3 kilojoules. That's how that works. That's Hess's law. All right, so we look up these values in table F, we plug it into this formula shown here, and everything works out just nicely. A couple more questions. If I wanted to write a thermochemical reaction with this data and figure out if it's exothermic or endothermic, how would I go about doing that? Well, I needed to pay special close attention, and we'll use bright, I don't know, what's a good color? Pink? I've already used pink. Bummer. Purple. To this value right there. All right, the sign of the enthalpy change is going to tell you whether or not it's exothermic or endothermic, and it's also going to tell you where to plug in that value in your reaction. So if it's negative, it's exothermic, and that means I'm going to be adding that value, and we use bright pink, as a product, plus 890.3 kilojoules. Common mistake, I've already mentioned it once before. Kids see that this is negative, and they either want to add a negative, or they want to they want to subtract it. All right, all that's really bad. Don't do that. You can only add heat to either the reactant side or the product side. I'm added to the product side because this is exothermic. I have a negative value here. All right, let's keep on going. This is also Hess's law. This is a different adaptation of it, I guess you could say. We can use known thermochemical reactions to calculate an unknown enthalpy change of a reaction. So here, these problems here, these are known enthalpy changes with those reactions that are given. There are 3 of them. This would be in the problem. This is not something you would have to, look up or figure out on your own. You're given that information. We're going to use those 3 to figure out this unknown enthalpy change. And if we look close to this thing right here, that stands for the heat of formation of a, what's it called? Standard heat of formation. There we go. That's a standard heat of formation. Look at that little, value there. The little F is for the formation, and that little degree sign is a standard heat of formation. Okay? So we're actually going to be calculating the standard heat of formation. Looks like I've forgotten my little degree sign. We'll add that in there. That's for the standard state. So the little degree sign, this is the state of matter at room temp. And this little F here is formation. And delta H, you already know, is the change in enthalpy. Cool. So we have our elements that make up this compound in their standard states, solid, gas, and this is gas. So that meets this requirement. And I know it's a heat of formation because I'm using carbon and hydrogen to make CH4. So everything works out in terms of that calculation. Anyway, let's get back to it. We want to calculate our standard heat of formation. We're going to use these given reactions and the enthalpy changes that are actually given as well. Looking at these, this might seem a little scary. That's just a standard heat of combustion. All right, I can add any enthalpies together. It doesn't have to be all formations or just enthalpy changes or combustion. They all work together. They're all the same basic idea. Okay, now back to the actual problem. What we're going to be doing is using these known values to calculate this unknown value. All right, so our overall goal is to calculate our standard heat of formation here. If we look, there are some similar pieces. Like I have some carbon here and I have some carbon here. I have some hydrogen here and I have some hydrogen here. And I have some CH4 methane here and I have some methane here. So the pieces of the puzzle there, what's a little bit worrisome though, is you notice that there's also other pieces of the puzzle. So right now, these 3 equations don't perfectly match up with this unknown equation. So I need to manipulate them so that they all match up all nice and even. Let's start with this carbon. Does the carbon shown here match up with the carbon shown here? Yeah, looks like I have 1 mole of carbon reacting, and I have 1 mole of carbon reacting. So far, so good. Let's go to the next one. Does my hydrogen here match the hydrogen here? No, it looks like I need double the amount. So to fix that problem, what I'm going to do is take this known thermochemical reaction and multiply the entire thing times 2. That would give me the same amount of hydrogen reacting as in my known to my unknown. Our last piece of the puzzle, let's take a look. We have our CH4 here and our CH4 here. Are those the same? Do these match up? Well, it's still 1 mole, but up top here, this is a product, and down here it's a reactant. To fix that, what I'm going to do is take my entire chemical reaction again, and now I'm going to flip it. I'm going to make my reactants my products, my products my reactants. If I do that, it's going to change from an exothermic reaction to an endothermic reaction. Let's take a look at what those changes look like. All right. So the first one I didn't have to do anything to. That's still exactly the same value here. My next one, I multiplied the whole thing times 2, if you remember, and now all the values are multiplied by 2. My last one, I had to do a flip, and now our reactants are our products are reactants, and take a look at that enthalpy change. It's now positive. Now it looks like all 3 of my reactions hopefully will add up to this unknown reaction that I'm looking for. All right, so I'm going to zoom out a little bit. You guys can see it. Here's my unknown again up here, and I'm trying to make these 3 equal that unknown. So my carbon's good, my 2 hydrogens are good, and my methane's good. All of those are in the right location in the right amount. Let's see if the other components cancel out. Now, just like net ionic equations, if you have the same thing on both sides of the equation, you can cancel them out. So here I have CO2 as a product, and I have CO2 as a reactant. Those cancel. Here I have 2 oxygen moles here, and I have 2 oxygen moles here. Those cancel. And then finally, I have 2 moles of water here, 2 moles of water there. Those cancel. What's left here is our unknown reaction, shown here. Because now all those 3 equations, when I add them together, they equal my equation that I'm looking for, I can add my enthalpy changes together, and that will equal what I'm looking for up top here. My change of enthalpy, in this case, is standard heat of formation. And that's my answer. That's how that goes about doing it. All right, we got one more thing to cover, and then we're done. This one looks like a big, fun, scary problem. So I need to calculate the enthalpy of the reaction. All right, that's our overall goal. That's calculating enthalpy. That's what this whole lecture is about. Believe it or not, you can solve this 2 ways. I've given you all these equations, so we can try to manipulate those equations to equal this unknown equation here, and then we can just add all these values together. Or I can use the other adaptation of Hess's law, in which I find out the standard heats of formation of all the components of the reaction, and I use that, Hess's law, which is the sum of your products minus the sum of your reactants, and that'll give you the enthalpy change of the reaction. And that's like this formula right here. All right, now let's do it by first using these knowns and make those equal this unknown up top. And then we'll solve it the other way as well. So I'm going to go ahead and look at it piece by piece. So I'm going to start with orange and find my ammonia here, my NH3. Do I see any ammonia? All right, here it is. Here's my ammonia. Now it looks like it's on the wrong side of the equation and I don't have the right amount. So that means I'm going to have to take this entire equation, I'm going to have to flip it so that my products are now my reactants, and I'm also going to have to multiply it by 2. And then it would match the unknown. Next, we got 2CH4. All right, where's the CH4? Here it is. All right, same situation. It's a product. I need it as a reactant, and I need double the amount of it. So I'm going to take this entire reaction, I'm going to flip it, and I'm going to multiply it by 2. Cool. That would fix that component. Let's see our next one. We need 3 oxygens here. Oh, geez. Okay. The only place I see oxygen is down here, and there's only a half. All right, so to fix that one, well, it's a reactant. That's good. I don't have to flip it, but I'm going to have to take the entire thing and multiply it by 6. That would change that half into 3 moles, and that would work out. Let's keep on going. I have my 2HCN here. All right, where's that? That's a product. Here it's a product too. All right, awesome. That's great. That's I don't have to do my, oh wait, I have double the amount. All right, so I gotta take this whole thing. I got to multiply it by 2. All right, and that would give me double the amount. And our last component, we'll use purple. Here's my H2Os. Do I see any H2Os anywhere? All right, here it is. Here's my water. All right, I need 6 of them. Oh, but I've already multiplied this whole thing by 6. So by fixing the oxygen, I've also fixed my waters, and I'll have the correct amount in both of those. All right, so I would have to change all this data here before I add it together. The first one, I'd have to make it positive and multiply by 2, right? Times 2. And the next one, I would have to make it positive and multiply by 2. This one, I got to multiply by 2. This one, I got to multiply by 6. And when I add those all together, after those changes, I should get my right answer. The right answer is negative 1,211.82 kilojoules. Woo, that's a lot. Okay, now, you might be asking yourself, how do I solve it using just the formulas? Because Estes said, you could do this both ways. Well, I use the heats of formation. Okay, so I need to find the heats of formation. And if I paid close attention to these units, you might notice that, believe it or not, I've given you all the heats of formation, and I don't have to look up anything. Isn't that nice? Here are all your heats of formation. I've given them to you. Take a look. Here's my NH3. That's right there. That's that heat of formation. Cool. Here's my CH4. That's right there. That's that heat of formation. Matches. Here's my HCN. That's its heat of formation. Matches up. And finally, my H2O. That's its heat of formation as well. So those values were all given to you. This O2, remember, that's a free element. Its heat of formation is 0. I don't have to worry about it. I do have to be careful here. For all those heats of formation, I would still have to multiply them by the right amount of moles. So here I'm multiplying both of those by 2. My third one, like I said, this one's not involved in my reaction. I don't have to worry about it. This one down here, I got to multiply that by 2. And this last one, I got to multiply by 6. Then I would plug it all into this formula, which we've used before. And you should get the same answer. Everything should check out. All right, that's your lecture on calculating enthalpy. Hope you enjoyed it.